This video is a deliverable of the European Interreg HyMoCARES project. It synthesizes the main results and some methodological developments to monitor the morphological effects of the river restoration actions that took place on the two French case studies, which are the Buech and the Upper Drac. More details can be found within the final report of the WP3 about these case studies. To present the restoration actions which were conducted on these case studies, it is important to introduce the general context of river management, and in particular, sediment management in the Alps. Indeed, several factors have led to coarse sediment depletion within rivers over the past. Extraction of gravels, dams, and embankments, within a context of reduction of upstream inputs which are related to reforestation and the climate change associated with the end of the Little Ice Age. In the context of the WFD, the achievement of good ecological status is required, and for alpine rivers, this objective can be reachable thanks to the restoration of the sediment continuity. One possible solution is therefore in this context to re-inject artificially sediment in order to restore this continuity. Two case studies located in the southern French Alps, the Buech and the Upper Drac, which are two gravel bed rivers, were restored with sediment replenishment actions. The morphological changes associated with these actions were monitored during the HyMoCARES project. The Buech is a gravel bed braided river draining the southern French Pre-Alps, most of its catchment being included in the Hautes-Alpes department. It is one of the major alpine tributaries to the Durance River, with a confluence at the city of Sisteron. The study ridge is located close to the city of Serres, downstream from the EDF dam of Saint-Sauveur, built in 1992 at an elevation of 640 meters above sea level. This ridge drains a 836 square kilometer upland catchment with a maximum elevation of 2,709 meters, which is the Pic de Bure in the Dévoluy Massif. The catchment geology is exclusively composed of sedimentary rocks, mainly of Jurassic and Cretaceous ages. Outcroppings of Cenozoic rocks are only marginally observed upstream of the city of Veynes. The lithology is dominated by alternating sequences of marls and limestones, which are typical of the southern Prealps. Glacial deposits from the last glacial maximum are only marginally observed in the catchment, mostly along the upper part of the eastern Petit Buech branch. However, considerable quantities of loose superficial debris are present in the subcatchments draining the Dévoluy Massif, where Cretaceous limestones sensitive to frost cracking supply massive talus slope deposits. The climate is Mediterranean with a mean annual rainfall of 800 mm. Heavy rainfalls typically occur during autumn and secondary during spring. The hydrological regime is also influenced by a moderate spring snowmelt. The 2.2 km study ridge presents a mean active channel width of 180 meters and a mean channel slope of about 1%. The study ridge extends from the Saint-Sauveur Dam down to the confluence with the Torrent de Channes, a left bank tributary to the Buech, joining the main stream near the village of Montrond. The channel morphology is a succession of segments characterized by wandering and braided patterns. The dominant substrate is composed of gravel-sized sediments with a D50 of 20 mm. D84 is about 40 mm. Although the ridge is included in an about 1 km wide alluvial floodplain, the lateral confinement related to roads or bedrock outcrops is important. Well-preserved patches of alluvial forest are only observed in the right side of the channel immediately downstream from the dam and in the left side downstream of the confluence with the torrent de Chane. Most of the floodplain is occupied by cultivated lands. The hydrological regime of the ridge is impacted by the Saint-Sauveur Dam, which diverted more than 75% of the natural flow. The ecological flow, or E-flow, downstream of the dam does not exceed 2.5 cubic meters per second. Illustration on the left are a view of the Buech River along the restored ridge, an aerial photo of the reservoir of the Saint-Sauveur Dam with the leisure center called La Germanette and the Saint-Sauveur Dam. The Upper Drac is a gravel-bed braided river draining the southern flank of the Écrin Massif, a geological unit belonging to the Alpine Outer Crystalline Massif, the northern flank of the Dévoluy Massif, which is a part of the sedimentary Southern Prealps, and the Flysch Thrust Zone, composed of Cenozoic sedimentary rocks. The entire catchment is included in the Hautes-Alpes department, and the headwater catchments of the Drac Blanc and Drac Noir are included in the Écrin National Park. The Drac is one of the major alpine tributaries to the Isère River, with a confluence at the city of Grenoble. The study ridge is 3.7 km in length, located at an elevation of 1,000 meters above sea level, and it drains a 340 square kilometer upland catchment with a maximum elevation of 3,441 meters, Le Sirac, in the Écrin Massif. This ridge presents a mean active channel width of 110 meters and a mean channel slope of about 1%. The catchment geology is composed of a complex assemblage of crystalline and sedimentary rocks. Metamorphic rocks, mainly gneiss, are located in the upper catchment of the Drac Blanc. The rest of the catchment is underlain by sedimentary rocks from Jurassic, black marls, Cretaceous, limestones, and Cenozoic, sandstones, ages. Imprints from the last glacial maximum are widespread in the catchment, with important till deposits on hill slope and paraglacial sediment in the valley floor. Of particular importance is the presence of lacustrine deposits in the valley floor related to the obstruction of the valley by the Sèvres Glacier during Vieuxmian phases of glacier recession. These clay deposits are covered by the thin contemporary alluvial fill of the Drac River. The climate is characterized by a mean annual rainfall of 950 mm. The hydrological regime is influenced by a strong spring snowmelt. The study ridge extends from the Champsaur Leisure Center to the village of Saint-Bonnet-en-Champsaur, 3.7 km, in particular to the Fish Pass along the Drac River, which is presented on the picture on the left. The channel morphology is an artificial wide and shallow channel with a rectangular cross-section recreated by the restoration project. It is expected to rapidly transform into a braided channel. The dominant substrate is composed of gravel-sized sediment with a D50 comprised between 40 and 80 mm. This ridge is included in a 300 to 400 meter wide alluvial floodplain confined by alluvial fans and landsliding deposits. well-preserved patches of alluvial forest are only marginally observed along the channel. Most of the floodplain is occupied by cultivated lands. The main proximal sediment source of the restoration ridge is the well-preserved braided corridor of the Chabot Plains, located 3.5 km upstream from the ridge. A secondary sediment source is the Brutinel Torrent, a left bank tributary to the Drac, draining the Dévoluy Massif and forming an alluvial fan at the confluence with the Drac. This tributary joins the Drac in the middle section of the restored ridge. Distal sediment sources are mainly composed of small active debris flow torrents of the Drac Blanc and Drac Noir catchment. Like most of alpine braided rivers in France, the Drac has been highly impacted by intensive gravel mining since the late 60s, and this activity stops only very recently, 2012. On the Buèche, gravel mining was also an important activity, and the sediment transport continuity has been altered by the dam. These anthropogenic activities, associated with the general context of sediment supply depletion mentioned in the introduction, caused severe alterations of the channel morphology and sediment transport. This deficit of sediment induced a strong narrowing and incision in the active channel. On the Drac River, incision of the channel progressed rapidly into a very sensitive lacustrine clay deposits, simultaneously with an intense regressive erosion, and the active channel width narrowed strongly. The graph on the bottom shows the strong narrowing of the active channel between the 50s and 2011. These morphological changes had dramatic consequences. The levee protecting the artificial pond of the Champsaur Leisure Centre was at risk of erosion. The lowering of the water table had consequences on the riparian forest mortality, and aquatic habitats were highly altered due to the loss of gravel substrate and to the expanding clay outcrops. On the Buèche River, gravel mining and the construction of the dam caused an important deficit of sediment and had strong impacts on the sediment continuity. Although the Saint-Sauveur Dam is equipped with 3 flood gates, allowing some sediment transport continuity during floods, most of the coarse sediment are trapped in the proximal part of the reservoir. As early as 1993, only few months after the dam commissioning, the formation of an entrenched single-thread channel in the former braided corridor downstream from the dam was observed, channel narrowing and channel degradation. The incision of the channel is known to be locally controlled by bedrock outcrops and the formation of the coarse surface layer interpreted as exhumed proglacial deposits from the last glacial maximum. The strong narrowing of the active channel between the 50s and a recent date due to the combination of anthropic pressures is illustrated on the right with aerial photos. The restoration project of the degraded ridge downstream from the dam includes an important operation of artificial gravel replenishment of 44,000 cubic meters implemented in September 2016 and funded and supervised by the power plant company EDF. Replenished gravel was directly dredged from the alluvial fan of the Buèche, forming into the proximal part of the Saint-Sauveur reservoir. Gravels were deposited along a 400-meter ridge downstream from the dam by the creation of 2 gravel berms on each side of the main channel. To facilitate the remobilization of the left side berm, a trench was cut into the deposit. A schematic cross-section of the replenishment action is presented on the bottom right of the slide. The general objective of the restoration project is to improve the hydrogeomorphic conditions of the degraded ridge downstream from the dam by an artificial increase of the coarse sediment supply to the ridge without any other intervention. A complementary objective is to reduce the flooding risk upstream from the dam by dredging the aggrading alluvial fan that progrades into the Saint-Sauveur reservoir. This accelerated sediment deposition represents a threat for the Germanet Leisure Center located on the left side of the reservoir. Expected restoration effects are the reversing of the channel incision trend, the increasing of habitat heterogeneity, and the improvement of the ecological status of the river. This is an illustration of the breach site after the sediment replenishment with the two gravel berms on each side of the main channel and the trench cut in the deposit on the right of the picture. The restoration project of the degraded ridge near Saint-Bonnet was implemented between November 2013 and April 2014 and consisted in the creation of a new wide and shallow channel using 355,000 cubic meters of coarse sediment, mainly from adjacent alluvial terraces and other complementary sources, as illustrated with aerial pictures on the bottom left of this slide. This is an operation of channel widening using a design 100-meter wide rectangular cross-section associated with a general rise of the bed level. A 1.65-meter high grade control weir was built at the downstream end of the restored ridge with a fish pass. These works were funded and supervised by the French Water Agency, the local basin authority, Communauté de communes du Champsaur, the Hautes-Alpes Department, the Provence-Alpes-Côte d'Azur region, and the European Union, with a total cost of about 5 million euros. The general objective of the restoration project is to recreate a braided channel corridor. A complementary objective is to avoid the destabilization of the right side dike protecting the artificial pond of Champsaur. Expected restoration effects are the spontaneous recreation of a braided channel, the increasing of habitat heterogeneity, and the improvement of the ecological status of the river. On the top, this is an illustration of the restoration works with the sediment remobilization from the terraces, and on the bottom, the creation of the fish pass and the canyoning pass. For both case studies, the physical monitoring combines a bedload tracing program using active ultra-high frequency RFID technology to monitor the transport velocity of sediment, time-lapse cameras to produce a high-frequency qualitative survey of the channel changes, and repetitive high-resolution topographic surveys of the restored ridge with LiDAR technology in order to assess sediment balance. Some UAV campaigns with visible camera were conducted in 2017 and 2018 for the monitoring of physical habitat changes. Other ancillary field surveys were also done for specific data analysis, bedload transport computation, bathymetric correction, and georeferencing of the data. About the morphological effects observed just after the restoration works, we could say that about half of the injected volume of sediment was remobilized on the Buech Ridge only 3 weeks after the restoration works, thanks to a large flood event of 5-year frequency. The picture on the right illustrates the morphology just after the flood. On the Upper Drac, some low-flow channels started to form on the upstream part of the restored ridge, as illustrated on the picture on the right. Repetitive topographic surveys of the restored ridge, DEMs, were overlaid to produce change detection maps. These DEMs are derived from 3D point cloud, 3D point to TIN to DEM, from airborne LiDAR surveys. Prior to this subtraction step, a crucial step of realignment has been conducted in order to fix the systematic error due to point cloud georeferencing and to have a more accurate sediment budget. After these steps, DEMs have been produced into Cloud Compare software and the rasters subtracted within ArcGIS, like illustrated on the figure on the left for the Bueche River. In the replenishment ridge, the topographic differencing between the LiDAR surveys of November and December 2016 shows a gross erosion of 25,450 cubic meters and a gross deposition of 7,600 cubic meters. This negative sediment balance is clearly driven by berm erosion. Indeed, 52% of the initial berm volume has been eroded during the flood. The replenishment ridge shows a much higher morphological activity in the right side of the channel, where most of the flow was concentrated. Erosion was very important for the right bank berm, 6,450 cubic meters, referred as BU1. The left bank berm in direct contact with the active channel, BU2C, has been also strongly eroded, 14,100 cubic meters. Only 1,550 cubic meters of erosion was observed for the berm on the left side of the trench, referred as BU2A. Bank erosion of a log terrace accounted for the remaining 2,800 cubic meters of sediment loss. A deposit of 800 cubic meters was observed along the trench, showing that bedload transport was active in this artificial secondary channel. The remaining 6,800 cubic meters of deposition are homogeneously distributed over the low-flow channel of the replenishment ridge, which exhibits a 0.5 meter aggradation after the flood. This clearly shows that a significant bedload volume crosses the dam during the flood. Sets of active ultra-high frequency RFID tags inserted into artificial gravels of similar size and density of natural gravels have been deployed to characterize the residence time of gravels in the restored ridge and to evaluate their virtual velocity. Distances of travel are computed by comparing the position of the tags between field detections. A set of 148 active tags has been deployed upstream of the dam to evaluate the sediment transparency and to constrain the travel distance of the re-injected gravels downstream of the dam. We obtained a 71% recovery rate of RFID tracers. Almost all of the recovered tracers were displaced during this period, n equal 100. Many tracers crossed the dam, 19.6%, n equal 29, whereas others not, 51.4%, n equal 76. Most of them stopped their course in the alluvial fan, 32.9%, n equal 58. Mobile tracer travel distances range from 12 to 3,406 meters with a mean value of 1,020 meters. All the investigated grain sizes have been displaced during the flood and no grain size effect on transport distances was observed. Frontrunners deposited downstream the confluence with the Torrent-de-Chêne in a ridge where bedload sheets with avalanche faces were observed just after the flood. The cumulative frequency of transport distances shows that 50% of the tracers traveled a distance greater than 900 meters and that a rapid decline of tracer frequency occurs at a transport distance around 1,700 meters. Long profiles have been studied from the analysis of LiDAR data from the November 2016 flood. Downstream the replenishment ridge, the longitudinal distribution of active channel bed level changes shows a much higher morphological activity in the first few kilometers downstream the dam, up to a distance to 3.5 kilometers, and a lower activity further downstream. This is a first observation suggesting a strong channel response to sediment replenishment. The classic sediment balance equation and the cumulative distribution of tracer transport distances were combined for assessing the downstream propagation of the sediment wave induced by the sediment replenishment operation. By considering sediment loss of the replenishment ridge, it appears that 25,450 cubic meters of gravels have been supplied to the downstream reach of the Bush River, mainly by lateral erosion of artificial berms, 22,650 cubic meters. The application of the sediment balance equation along the reach, where significant net deposition is observed, provides a way to reconstruct sediment transfers of the Bush downstream of the dam during the November 2016 flood. The only term of the equation that has been constrained is the storage change along the ridge, net deposition of 20,700 cubic meters. By considering bedload transport computation using the flood hydrograph at the downstream end of this ridge, 12,000 cubic meters, it is possible to evaluate bedload inputs at 32,700 cubic meters. Inputs are divided into berm erosion for 22,650 cubic meters, bank erosion 2,800 cubic meters, and the back-calculated bedload passing through the dam 7,250 cubic meters. Since a deposited volume of 7,600 cubic meters is observed along the replenishment ridge, it should be added to the 7,250 cubic meters that passes through the dam, giving a total bedload transport crossing the sluice gates during the flood of 14,850 cubic meters. This value corresponds to 35% of the mean annual bedload yield upstream of the dam and 74% of the mean bedload yield downstream of the dam. The bed level evolution and 2D change detection map from sequential LiDAR data both reveal a dominant pattern of channel aggradation along a 2.5 km ridge downstream of the dam. Further downstream, another sediment deposition zone is observed at a distance of 3.5 km, but this distal aggraded ridge is likely not related to the sediment replenishment operation. The cumulative frequency of bedload transport distances observed during the flood indeed shows that 90% of the tracers deposited at a distance lower than 2 km. When this cumulative frequency is used to redistribute the effective bedload supply from the replenishment ridge, which has been well constrained by sequential LiDAR data, it is possible to reproduce that observed cumulative deposition curve up to a distance of around 2 km downstream of the replenishment ridge. The hydrological sequence of the Upper Drac since the restoration works has only showed some low-intensity snowmelt or autumn rainfall-induced flow events. Bankful discharge conditions along the restored ridge have not yet been observed until now. However, some morphological adjustments are visible and show a strong spatial variability in the active channel bed level evolution between 2015 and 2018 along the river length comprised between the Chabot Plains and the restored ridge. A set of 161 tags has been inserted in artificial gravels and deployed in the braided Chabot plain upstream of the restoration site to evaluate the bedload transit time from this major sediment source and the restored ridge. 4 tracer inventories have been done between August 2017 and September 2018. Results show a rapid dispersion of tracers between the Chabot plain and the restored ridge, with frontrunners already reaching the restored ridge only 20 months after their deployment, despite relatively low hydrological forcing. Recovery rates based on the total population of tracers are high, from 79 to 97%. Recovery rates from mobile tracers only are lower and strongly decline through the time, passing from 80% to 36% between the first and last inventories. It should, however, be mentioned that only a small fraction of deployed tags have been mobilized during the period. Those correspond to tracers deployed in or close to the main low-flow channel. Tracers initially deployed on gravel bars were much less mobile, since gravel bars in the Chabot plains do not show a strong morphological activity during the period. These observations confirm a strong bedload connectivity between the restored ridge and its main sediment source, which is an important condition for the maintenance of a restored braided pattern. A longitudinal analysis of the active bed level and DEM of difference between 2015 and 2018 are presented on the top and on the bottom left of this slide. It shows that along the restored ridge, an alternating sequence is observed between two aggraded ridges, D1 and D2, and two degraded ridges, E1 and E2. A gradation in D1 can be explained by sediment supply from the Chabot plain, and degradation in E1 is interpreted as regressive erosion in the proximal main channel of the restored ridge, induced by a break in slope in the initial restored long profile. A gradation in D2 is spatially linked with a zone of active channel width increase, which may have enhanced sediment deposition. The distal ridge E2 may have not yet been fed by the sediment supply from Chabot plain, as suggested by its degradation trend. DEM differencing during 2 periods after the restoration has been used to estimate the sediment budget of the Upper Drac from the Chabot plain to the restored ridge. The aggradation trend along the restored ridge is confirmed by the positive net volumetric change of the 2 periods. 2 upstream control ridges show the same trend during the 2015-2018 period. It should, however, be noticed that those budgets only consider the exposed area of the active channel, given that infrared LiDAR surveys do not account for the bathymetric relief of the channel. It is not excluded that the inclusion of the submerged portion of the channel into the net volumetric change would provide a stable or negative net change, since accretion of exposed gravel bars could have been partially or totally compensated by the entrenchment of the low-flow channels. If we synthesize the results about the morphological changes thanks to the bedload and topographic monitoring, we can notice that on the Upper Drac restored ridge, a promising trend towards spontaneous braiding recovery has been observed. Gravels are rapidly transferred from the first upper sediment source located in the braided Chabot plain. The flow facies and physical habitats are now more diversified. On the Bush Ridge, the restoration allowed the global aggradation and the limitation of incision, but no braided pattern has been observed yet. Effective transfer of gravel from upstream of the dam has been proved thanks to the tracing of sediment. The sediment replenishment took place just before a 5-year flood event, so this raises the question of the evolution of the morphology of the restored ridge without this big flood event. I will now present the results from the UAV survey. As mentioned previously, 2 UAV campaigns with cameras were conducted in 2017 and 2018, and the data were processed thanks to SFM photogrammetric techniques. It allowed to produce high-resolution point clouds and DEM. The processing of the data showed some geometric problems. Indeed, identical positions in 2017 and 2018 for stable elements shows errors that are spatially randomly distributed. In Z dimension, differences in elevation range from 2 cm to more than 1.5 meter. We try to identify the sources of errors, which could be due to the bad calibration of the DGPS and to the design of the survey, which were conducted at only 1/8 of flight. This led to not use the DEM produced with this photogrammetric technique for estimating the sediment budget. However, some other special information could be produced. Vasquez-Tario et al. 2017 proposed to use roughness indicators as a proxy of the substrate size. Indeed, the grain size measured on the field is strongly correlated with the roughness indicators. Consequently, we used this kind of indicator to produce a spatially continuous map of this proxy of a superficial grain size. We developed a methodology to empirically correct the value of bathymetry from field measures and used it to produce a DEM relative to the water level. The SFM photogrammetric process allowed to produce high-resolution orthophotos of 1-2 cm of resolution. These orthophotos were analyzed to extract automatically the fine sediments deposited on the gravel bars. Spectral and textural information were expertly analyzed and combined with a threshold on the proxy of the superficial grain size, which is the roughness indicator previously mentioned to exclude pixels that correspond to surfaces with a high elevation variability. It means the vegetation, dead wood, and large boulders. This binary map of fine sediment was restricted to terrestrial zones. The figure shows for each UAV campaign the thresholds applied on the orthophotos texture and spectral values, and the threshold applied on the roughness variance used to map the fine sediment patches. To summarize, the UAV campaigns allowed to produce high-resolution DEM and orthophotos, which have been analyzed to extract key indicators to characterize the physical habitats along the restored ridge. Here, the results that will be presented focus on the Upper Drac case studies. The 3 indicators calculated to characterize the diversity of physical habitats are the variance of the roughness indicator, which is correlated with the sediment size, the relative elevation to the water level, which can characterize the flooding dynamic, and the presence of fine sediment in the terrestrial zones. A direct analysis of these indicators is too complex to produce an automatized classification of the physical habitats with the standard statistical methods. Consequently, we choose to discretize raw indicators and then to combine them into a multivariate analysis in order to characterize the physical habitats. Variance of roughness, which is, as mentioned previously, correlated with the sediment size, was classified into 4 classes corresponding to quantile values of the distribution of 2018 values without considering 0. The distribution of 2017 and 2018 values is illustrated on the figure on the left. This discretization in 4 classes is illustrated on the right, showing that several grain sizes can be present on the same gravel bar. Values are very low because the roughness indicator was calculated in meters, but the meaning of the classes remains identical. The lower the variance of roughness is, the smaller the sediments are. The highest values group together some large sediment with pioneer vegetation and large wood jams. The second indicator taken into account to characterize the physical habitats is the relative elevation to the water level, which was discretized into 7 classes. It means 3 classes under the water level and 4 above, with the following class boundaries, which correspond to rounded percentile values of the composite distribution of 2017 and 2018 values illustrated on the left. On the right, the figure shows the 7 classes of relative elevation in meters. As the restored ridge shows a braiding pattern, the depth of the channels is relatively low, and all the pixels showing a depth higher than 35 centimeters were grouped together. As the fine sediments on gravel bars are already mapped as a binary map resulting from the analysis of several metrics, class 1 corresponding to fine patches and class 0 corresponding to coarse patches, vegetation and water, it means not fine sediments on gravel bars. We combine directly the 2 classes of this map with the 4 classes of roughness variance and the 7 classes of relative elevation which were presented in the previous slides. The logical combination of all the unique values of class allowed to distinguish a large set of classes, some being marginally represented. These classes will be called in this presentation the physical habitat types, to not be confused with the classes of the indicators which were discretized. The total number of physical habitat types is 40, as some combinations of the indicators are not possible. It means no terrestrial fine sediments considered under the water, and the resolution 1 square meter. This methodology was applied for 2017 and 2018 campaigns where the discharge of the Drac was at low flow and nearly identical for both campaigns. The extent was limited to the maximal spatial coverage available for both dates within the active channel. This map illustrates the 40 types in 2017 and 2018 grouped by aquatic classes, terrestrial classes, and terrestrial classes covered with fine sediments. No data areas correspond to poor quality data produced by the photogrammetric process, which were not integrated into the multivariate analysis, or to lack of data due to non-overlapping flights during the UAV campaigns. We used these 2017 and 2018 maps to compare the diversity of physical conditions for these 2 dates at the ridge scale. On the right, the frequency of each type, it means each unique combination of classes of the discretized indicator in the complex typology of 40 types, can be compared in 2017 and 2018. Many pixels change in this period. Only 15% of the pixels remain strictly identical with the same combination of indicator classes. Aquatic habitats remains aquatic for 24.6% of them, and 50.4% of terrestrial habitats remain terrestrial. A slight part of terrestrial habitats in 2017 became aquatic in 2018, about 10%, and reciprocally, aquatic habitats became terrestrial for 14% of them. The frequency distribution of physical habitat types are very close in 2017 and 2018. Some physical habitat types are particularly more frequent in 2017. Very shallow channels, it means those which are lower than 10 cm in depth with medium or high size of gravel, which are the types 10 and 11. And exposed bars between 0.35 meter and 1.2 meter above the water level and composed of boulders, the type 24. In 2018, shallow channels composed of gravel and exposed bars with medium grain size of gravels between 0 to 1.2 meter above water level are also more frequent. In 2017 and 2018, some physical habitat types are on the contrary less frequent, like channels showing a depth above 0.35 meter and exposed gravel bars 1.2 meter above the water level, which are less frequently inundated. We calculated a diversity indicator of these physical habitat types in 2017 and 2018. The values can be seen in the table on the left, which is here the commonly used Shannon index. The formula is given under the table. We can conclude that values are very close to each other in 2017 and 2018 when considering all the physical habitat types together and when studying separately aquatic and terrestrial zones. It means that low changes can be observed in terms of physical habitat conditions between these two campaigns. The proportion of transitional habitats decreased between 2017 and 2018 associated with the simplification of the breeding pattern. The number of channels decreased, some channels incised and some terrestrialized. The number of pixels of very shallow channels was divided by 1.78 and respectively exposed bars near the water level from 0 to 0.1 meter was divided by 1.25, while in the same time the number of pixels of shallow channels was multiplied by 2.54, respectively exposed bars between 0.1 and 0.35 meter above the water level by 1.08, respectively exposed bar between 0.35 and 1.2 meter above the water level by 1.22, and respectively exposed bar 1.2 meter or more above the water level by 2.78. All physical habitat types taken together, the average size of the sediments decreased between 2017 and 2018. The classes corresponding to low and medium values of roughness variance increased, respectively, from 7.9% to 10.2% and from 33.2% to 56.06%, while in the same time, the classes high and very high of roughness variance, it means showing the highest superficial grain sizes, decrease respectively from 34.5% to 22.2% and from 22.2% to 11.3%. Major changes are observed for medium roughness variance with aquatic physical habitats, a strong increase from 1.9% to 10.9%. And for transitional habitats with a strong decrease of the high and very high roughness variance classes, respectively 17% to 5.2% and 5.8% to 0.9%. Pixels corresponding to terrestrial habitats types covered by fine sediments do not represent pure coverage of fine sediments because of the 1 meter resolution. It might represent various proportion of coverage of fine sediments depending on which class of relative elevation to the water level and on which class of the roughness variance. For the relative elevation 1.2 meter above the water level, this proportion of coverage is really low, whatever the class of roughness variance is. The types combining low roughness variance and relative elevation to the water level between 0 and 1.2 meter correspond to fine sediment mixed with gravels with a proportion of coverage of fine sediment really variable. For physical habitat types combining medium roughness variance and a relative elevation to the water level between 0 and 1.2 meter, fine sediment are mixed with gravel to boulders, pioneer vegetation, and also wood jams. The types combining high roughness variance and a relative elevation to the water level between 0 and 1.2 meter correspond to fine sediment mixed with large boulders, pioneer vegetation, and also wood jam. A special analysis of the Shannon Diversity Index was conducted at the sub-reach scale. The reach was divided into 39 sub-reaches where previous topographic data were available. It means between 70 to 200 meters in length. It shows that for most of them, the diversity of physical conditions decreased between 2017 and 2018. However, we can distinguish more precisely three behaviors. For most, a clear decrease, a stagnation, and a net increase. I will present two examples here, one on a net decrease in the diversity of physical conditions, then one on a net increase. Here is an example of decrease in diversity between 2017 and 2018. On the top are the maps of the 40 physical habitat types, just under the maps of the relative elevation to the water level, and on the bottom the maps of the various classes of roughness variance. On the right part of the slide are the maps of fine sediment patches. What is noticeable is the increase in the proportion of terrestrial pixels, a lower number of class of roughness variance, which means that the distribution of grain size could be less extended in 2018 on the right than in 2017. And finally, the number of fine sediment patches is lower in 2018 on the bottom right of the slide. Here is an example of increase in diversity in the middle part of the restored ridge, which shows a really well-developed braided pattern. In 2017, on the top left of the slide, we can see that the diversity of physical habitat types is lower than in 2018. The maps of relative elevation to the water levels shows that the number of very shallow channels is lower in 2018 than 2017, and the depths of the channels are more important. It means that between 2017 and 2018, some channels have incised and some have been terrestrialized. The distribution of classes of roughness variance is also less extended in 2018 than in 2017, and it could be interpreted as a decrease of the grain size, in particular on the terrestrial area. Terrestrialization of some channels and decrease of the grain size is confirmed by the important number of fine sediment patches that appeared in 2018. Some outlooks for this work conducted within the HyMoCARES project are first to continue the monitoring on the case studies to evaluate longer-term morphological changes. About the method to characterize the physical habitats, some improvements are in progress. We would like to adopt several levels of characterization which could be useful for water managers and practitioners. For this, we have considered to vary the number of classes chosen for each indicator in order to have more or less physical habitat types in the created typologies. This number of initial classes should be designed thanks to the statistical distribution of each indicator. The created typologies could then be further analyzed in terms of size of each physical habitat types and their spatial variability. To conclude, the program HyMoCARES allowed to fund the monitoring of the 2 case studies with 2 UAV and field campaigns. The both operations of sediment replenishment on the French case studies are considered successful with a spontaneous breeding recovery and the limitation of incision. Many tools have been developed and validated, in particular for correction of the bathymetry, the mapping of the water channel and fine sediments, the extraction of the roughness indicator, and the relative DEM to the water level. And finally, the multivariate analysis is promising for characterizing the physical habitat's diversity at various detail scales, which could be really useful for water managers to assess the benefits of the restoration actions. Thanks for having listened to this online presentation. For more details on the case studies and their monitoring on the tools developed, please visit the HyMoCARES website.